So in this lecture, we are going to study the design of column for eccentric loading. We have already studied it for concentric loading. Now we are going to take it up for eccentric loading. Let's take a good example. Design a rectangular column for a load, that's dead load plus live load, both of 2000 kilonewton. Assume that there is a M30 grade concrete used and Fe 500 steel. The load eccentricity of the column is about 1 axis, that's its uniaxial. The column is as shown in figure. So first let us see, the column is provided to you that it's got a dimension of, this is 600 mm and this is 300 mm, 350 mm. Then it's also given to you that cover of the column is 40 mm, that's given. The ties that are to be provided or the transverse reinforcement, that's also given, are to be 8 mm in dia. So the first step here is covered. Now where did this come from, the dimensions? It's actually that the beam has already been placed, so the column dimension is thereby fixed. So now in this case, we are assuming that it's under a uniaxial eccentricity. Assume that there is uniaxial eccentricity in the column. Now for this column, you need to design it. You need to determine the, first of all, what we need to do is we need to check how much is the design strength of this column before we proceed towards the design of this column. Now, it's very important to determine the design strength of this column, because we don't know what is the amount of eccentricity that is acting on this column. So the first thing is that we need to determine the amount of eccentricity that this column is undergoing. So what is given to us is this, that one, you have B of the column is how much? It's 350. For example, I take B as the smaller dimension. D is 600 mm. Then what is also given to us is that FCK is 30 megapascals and Fy is 500 megapascals. Then what is to be determined is the area of steel. Now, if that's not given to you, the area of steel is not given to you, so it's very difficult then to first of all determine the strain profile and the stress profile of the section. So it's very difficult then to know the neutral axis of the section. So we will first of all assume that there is a particular amount of steel reinforcement that is provided for the section. Now, before assuming it's the steel profile, let's go through the steps of the design. If it was a concentric loading, what would be the first step? Step number one, fixing the dimension, that's done here. And step number two, what would be the step number two now? In this case, if the dimension is fixed, what is step number two? Load. Load is already given to you. What about the slenderness? Let's check the slenderness of this section. Yes, one thing is not given here. Let's have the length of the column is 3.5 meters. The slenderness of the column would be, if both the ends are fixed, would be 0.65 into 3500. That's the length, divided by the minimum of the two, 350. So we are calculating about the least sectional dimension, that is 0.65 into 3500 divided by 0.65 into 3500 divided by 350, 6.5. So in terms of slenderness, it's okay, it's a short column. Now, it's given in the question that you have to assume a uniaxial eccentricity here. So you need to calculate the eccentricity. But before going into that, we need to first of all calculate how much is the reinforcement. Either we assume it or we determine it on basis of the concentric loading. So step number two here. So here it's a short column. That's proved. Step number two, now you determine the longitudinal reinforcement. And the longitudinal reinforcement we determine based on the equation PU is equal to 0.4 FCK into AG plus 0.6 SC 0.65 into Fy minus 0.4 into FCK. Yeah. Now this is 1.5 times 2000 is PU This is 0.4. The FCK is 30. AG is 350 into 600 plus ASC. ASC you need to determine 0.65 into 500, 0.4 into 30. So ASC would be, yes, can you calculate this?
Sir, ASC is 313.
313. Let me check.
Yes, sir.
This is into 10 raised power into 1000. Yeah. It's 1533. This is 1533.546 mm square. Now, then you provide steel bars. If I'm providing 20 mm bars, each bar would be 314. Provide 25 mm bars. 22. Let's provide 22 mm bars. That would be 379. Each bar would have area of 379.94 mm square. So you would have ASC, the number of bars that you are providing, number of bars, that's 1533.546 divided by 379. That's around 4.04. So it's almost around 4 bars. It's almost 4. So you're providing 4 number of bars, 22 mm dia each. Then now you can fix the number of bars here. But the issue in this case of a column arises is that if I provide only 4 number of bars, after every 300 mm at least I have to provide a tie link. So I need 2 more bars at the center. So let me not go for then 22 mm bar. If I go for 16 mm bar, that would mean 200.96. That would mean 8 bars. uh, if I go for 20 bars, and 14, 5 bars. So you can provide 20 bars. What you can do is you can provide 4 number 20 bars and 2 number 16 bars. That would be 4 into 3.14 divided by 4 into 20 into 20, plus then you would have 2 into 3.14 divided by 4 into 16 into 16. So this total, the area provided would then be 3.14 divided by 4 into 20 into 20 into 4, 1256 plus, then you have 3.14 divided by 4 into 2 into 16 into 16. So that's 401.92. So you're getting 1256 plus this is 16.57.92 square. This is how you are getting. Now we have provided four number 20 bars. So these four, this, this, and this are 4 number 20 bars. And then I'll be providing 2 more bars at the center. Now these are essentially required because you need to provide the links at least 300 mm, and then you would have the tie ring like this, and further a link at this position. Now the rings are already given that you need to provide in the question. Rings at 8, that's 8 dia. So whatever the spacing between them, right now we are not concerned about the spacing between them. Now this would have been a case when we were doing concentric loading, axial short column. It is a short column. Whether it's axial, it's not completely axial. So the design has to be such that first of all we determine the eccentricity of this. The eccentricity that we determine by the code, that's different. That's the minimum eccentricity. Now where we have to check the actual eccentricity of this column. So first of all, what we are going to do is that we are going to first of all determine the design strength of this column. Now to determine the design strength, we need to determine the where is the neutral axis. So of the neutral axis is given in this question. Let us assume that for this question, this is also given in the question. Let this be given in the question. XU by D is 1.2. Now where would be the XU for this column? Now this is the column. If I take section about the depth D, this is a section about depth D. Now this is D, which is 600 mm for this column. Then we first of all need to check now these are the points where you have reinforcement. This point, this point. This is the center point of this column. Now if I draw the stress pattern for this column, it would be, first of all, let's determine the distances, these distances from this point up till this point. From the center, it would be 600 minus, calculate it here, 600 minus 40 is the cover, minus you have stirrups 8 mm, minus half of the outer bar, which is 20 mm, uska half is 10 mm, so that's 10, so it would be 50, 550, 542 divided by 2. 542 would be the distance from this point up till this point, so uska half hoga this much, which is 271. This is 271 mm. Now similarly, this is 271 from the center up till this point. You have the edge distance now. This would be 10, 850, 58. Right from here, from the center of this up till the end, the distance is 58. Similarly, on this side, it's 58. Right from here up till this point. And this dimension we already know is 300. B is 300, 350 mm from here till here. And we are also being provided with the there is stirrup 8 mm outside this boundary. Now if I have to first of all determine the profile, stress and strain profile of this, if I first determine the stress profile or the strain profile of this, the strain profile of this would be, because the load is, how is the load acting? The load is acting